Log on, tune in, find out. Another good idea from Cambridge.
So thank you very much. Thank you very much to the organizers for inviting me for organize this nice semester on Moduli spaces. So let me give you the plan of my talk. So first of all, I want to give some kind of introduction with some preliminary results and definitions in order to give you also some piece of motivation for those kind of works. Then, as a second section, I will give some kind of key results just for passing from a relative to an absolute setting. Where some work has been done already for this kind of problems. Then, as a third section, we will do a work example, and it's going to be apply these key results for the case of Weierstrass fibrations. And if times allow me, I will give you as a final sections what are the results that we got for abelian schemes and Fano fibration applying the same techniques. Okay, so results for abelian schemes and Fano fibration. Okay, so let's start with the introductions. So let me start directly with the definition of a relative integral functor in a quite general context. Okay, so let's assume that we have x over t and y over t, p and q, two proper morphisms of schemes, over a base scheme over t that in general is an arbitrary scheme, and for me arbitrary means of finite type and separated, or a scheme that I will consider will have these two properties. For me it's arbitrary enough for the moment. Okay, so no more condition here or assumed on the total spaces x and y, nor on the fibers of P and Q that could be, of course, singular schemes. Okay, suppose that you have an object in D minus of the fiber product of these two schemes. So this denotes the derived category of bounded below complexes with quasi-coherent cohomology sheets. They are just quasi-coherent, with quasi-coherent cohomology. So in this situation, you can define the integral functor, the relative integral functor corresponding to this object, which is called the kernel. And I will use this notation in order to say that this goes from d minus of x to d minus of y. And the definition is the same of a Fourier-Mukai transform. So you have here the fiber product, the two projections, P1, P2, here your P and Q, T, and let us denote this row. So given a complex here, then you pull it back to the fiber product, and P1 star of E, tensor it by the object that you have fixed, your kernel, K, and then pull it back to Y by means of P2. So the definition is the same, just we have to consider all the functors as derived functors because our morphisms could be not flat morphices. So anyhow, all of these functors are well defined. So the first remark is the following. So notice that, of course, by means of a Bayes change, any integral, relative integral functor is isomorphic to one absolute integral functor, because we have this isomorphism where I is the natural immersion of the fiber product into the direct product. So relative Fm, or absolute, and by absolute I mean that the kernel is in the derived category of the direct product and not on the fiber product, absolute Fourier-Mukai functor. But of course, the converse is not true. And in fact, as we are going to see later, those functors that have good properties are those that are relative Fourier-Mukai functors, because they have good properties in order to study moduli spaces. No? Okay, then as a second remark is that in an ideal situation, I mean for me, is good hypothesis is in the case of smooth and projective varieties in this world. So thanks to Serre's theorem, we all know that any coherent shift has a finite resolution by locally free shifts of finite rank. So this means that the subcategory of perfect complexes is in fact equivalent to the whole derived category of bounded complexes with coherent cohomology shifts. So we have this equivalence. Of course, since we are allowing that our schemes are singular, this is no longer true, no longer true for singular schemes, where in fact this is a proper subcategory. It's contained, but it's not equal, not equivalent to that one. In fact, you have just to consider the structural shift of a singular point. This is not a perfect complex for X singular. And this is in fact one of the main difficulties that one has when we are trying to work with derived categories for singular schemes. They are complexes that are not perfect, and then you have to work not just in the bounded derived category of coherent shifts, but you have to allow unbounded complexes. Anyhow, also for unbounded complexes, all the derived functors, the right derived functors, the direct image, the inverse image, all of them, they were constructed by Spalsenstein. I don't remember how to explain Spalsenstein. We are working in 1988. And just assuming that your morphism in the first one is locally projective, so you have that your functor in fact can be extended to a functor between the whole derived categories from dx to dy. But in general, of course, even if your kernel belongs to the bounded derived category of the fiber product, it is not true in general that this functor sends bounded complexes to bounded complexes.
So dx without a bracket is just the unbounded derived category of all X modules?
Yes, this one is just with quasi-coherent cohomology. Quasi-coherent cohomology shifts. Okay? Okay, so there is a technical condition in order to fix this. Technical condition that is the notion of being of finite homological dimension over the base. Let me give you just the definition. So suppose that you have a morphism of schemes, and an object here in set. So the object is said to be of finite homological dimension over the base, over G, if it satisfies that when you tensor it for any complex coming from the base, this one, so it has to be bounded for any n bounded. No? It's bounded for all n in here. So let me give you just some examples. For instance,
This is what they call a relatively perfect mass G, right?
it's almost that one in good condition for projective ones. Okay. So for instance, if your base is a point, the spec of a field, this is satisfied for any complex. So any E belonging to the bounded derived category is of finite homological dimension over T. If your morphism, for instance, is the identity, so this is just the notion of perfect complex. So finite homological dimension is just perfect complex.
In fact, I think if you have a flat vibration, then globally perfect means this relatively perfect plus perfect with fibers.
Yes, I think so. Okay. For instance, if the morphism is projective, F projective, and you have very ample divisor, no? This is to say is finite homological dimension over the base, if and only if not just the push forward but of it, but of all tensor by any integer number is perfect. It's perfect for all R. Okay, so some examples of these objects. Okay, so with this notion, so we got the right conditions on the kernel. So conditions on K for the corresponding relative integral functor. First, to map bounded complexes to bounded complexes. And this is just that your kernel that lives in the fiber product is of finite homological dimension over the first factor, over X. And moreover, since we are interested in functors that are equivalence, so you need to know sometimes when your functor has an integral right adjoint. So in general, any functor has a right adjoint by Grothendieck duality, but it has not to be an integral one. So in order to be an integral right adjoint, and moreover that this adjoint satisfies also this condition with a property, this is A, this is B, then the condition is that the kernel has to be of finite homological dimension, not over the first, but over the two factors, X and Y. Then you have a right adjoint, and this is an ice adjoint. This again an integral functor. Okay? Okay, but this is all of them are technical conditions that are not so strained. No? For instance, you have that both P and Q are projective, for instance, projective morphism, and you have already a functor that is an equivalence of categories between these two. Just from the fact that this is an equivalence, you deduce that the kernel is of finite homological dimension over the two factors. So for equivalence, everything is satisfied. K has finite homological dimension over X and Y. This is immediate from the fact of being an equivalence. By the way, those integral functors that are equivalence is what we know as Fourier-Mukai functors, relative Fourier-Mukai functors. No? Relative Fm is just that it is an equivalence. Okay? Okay, so another important feature about these functors is that they come in families. So what I mean by this? So suppose now you have your scheme and your fiber product here in this general contest, and suppose that you have a base chain, any base chain. Then you can consider the fiber product over D. Let us use this notation. Here you have your kernel K, then you can pull it back all in the derived category, and you can construct a kernel here. It's just the pullback of your kernel K. So that gives you, for any base chains, a functor that I denote like this. Phi B is the functor corresponding to this kernel. Okay? This goes from the category of XB using the same notation. No? Here you have X, here you have F, B, and XB is just the base chain. This is Fx. Goes from here to here. And with very mild conditions, so yes, assuming either P or the base chain is flat, you have a nice formula, a nice base chain formula. No? If X or B is flat, either is flat, then you have the first is that everything behaves very nicely. No? If K is finite homological dimension over X, for instance, then the base chain has also this property over XB. Everything is all right. And moreover, you have that you have a complex in GV here. You put it back to XB and you transform by the new functor. Then it's the same that first you transform G and then you pull back by the other morphism. So it's a very nice formula of compatibility of internal functors. And this is in fact, this formula is in fact one of the reasons that give us the first piece of motivation in this talk. I mean, this formula tells us that these kinds of functors, relative functors, behave very nicely with moduli spaces. No? So, some kind of motivation for the talk. If you have an integral functor from here to here, relative or absolute, I don't mind, with two properties. The first property is that the integral functor, we just denote it phi, forgetting the kernel. So the first property is that phi transforms shifts into shifts up to translation. Up to shift. So that means, no, another way that appears in the literature is that any coherent shift in your first scheme is what it is called WIT I for phi. No? Just meaning that when you transform the sheaf, what you get is not a real complex, but just a sheaf. Maybe shifted by the degree I. Or this is a sheaf on Y. Your functor has this property, and moreover, it preserves the semi-stability condition. Moreover, phi preserve semi-stability. In the sense that if you have a sheaf with some fixed invariance, and then you transform, you get this sheaf on Y that is also semi-stable, if E is semi-stable. Then you get from phi a morphism of schemes from the moduli space, relative or absolute, doesn't matter too much, depends on your scheme, if it is relative or absolute, with some of sheaves. This means semi-stable sheaf on X over T, relative modulus Simpson space, with some Hilbert polynomial P to the moduli space in the scheme T over T with another Hilbert polynomial P hat. So in general, this morphism is not injective nor suggestive. So depends, could be neither. But if your functor is an equivalence, if phi is a Fourier-Mukai transform, and moreover, the inverse of this functor has both properties, 1 and 2, then this morphism, which is a morphism of schemes over T in the relative situation, this morphism is an isomorphism. You get an isomorphisms as schemes over T. So with this machinery, you transform your moduli problem into another moduli problem that hopefully will be easy, or maybe if you are very lucky, you know the solution for this moduli problem. Okay? Okay, so this is a good motivation to study the group of relative Fourier-Mukai transform of the derived category of X, where X is a scheme fiber over the base scheme G. Okay? At least it's a machinery to study our moduli spaces. And of course, I have to say also that imagine that your variety for a moment, that is an absolute variety. Okay? So in the case that X is, let's say, projective variety over the spectrum of a field. So not only that one, the Fourier-Mukai of this one, but the whole autoequivalences of the derived category. This is a group, as Daniel explained us last week, that is acting on the space of stability conditions. This is acting on the space of stability conditions of X. No? So this is a good reason also to take a look to these groups. So let me very quickly to make an overview about what is known about this group and this subgroup in the case when your variety is over the spectrum of a field, and then to pass to the relative situation and to see what we can do there. Okay? So in the case that you have a variety over a field, some things are new about these groups. Huh? So for instance, always this group, the group of autoequivalences of the derived category, it contains always the trivial ones, no? That I denote like this. And these are just the ones given by the automorphisms of the variety, tensored by line bundles, and shifted by some degree. Okay? In fact, if X is smooth, there is a classical result by Orlov that tells you that any autoequivalence is a Fourier-Mukai transform. So is the group this one. Okay. This was done by Orlov, classical result that any fully faithful factor is representable by some object. And this result has been recently generalized. This is what for X smooth. This has been generalized by a work by Ballard for any projective scheme. Generalized for any projective scheme. So for any projective scheme, any autoequivalence of the bounded derived category is a Fourier-Mukai transform that could be absolute. I mean, even if your variety is fiber over a weight, the kernel of the Fourier-Mukai transform is only now to be in the derived category of the direct product, not on the fiber one. Okay, just for absolute factors. For unprojective schemes, there is some result by Orlov, some work also for quasi-projective. Schemes. But it's not clear, it's a now, in fact. Huh? Orlov proved that you have an equivalence of the whole category from dx to dy. There exists an object, there exists k in the derived category of the product such that the corresponding factor is an equivalence, but in general it's not the original factor. Okay? So, such that, it's a noun. This is an equivalence, but these two only coincide when they are applied to perfect complexes. In general, there is not a canonical isomorphism between this one and this one for quasi-projective schemes. Okay? Oops. So, in general, for more general schemes, it's a now the result. Nobody knows if any factor is representable or not. Okay. So, what else? Okay, there are some cases. Second. P hat is the Hilbert polynomial of E hat. Okay, when you transform. Okay. So this group has been determined in some cases.
So you also automatically assume that a shift with a Hilbert polynomial gets always taken, that this transform is also considered kind of, if it takes one shift with one Hilbert polynomial to another shift, another Hilbert polynomial.
The Hilbert polynomial is fixed, and every shift with this Hilbert polynomial has to be WIT for the same index. Okay? Okay. Yes? Okay. Okay, so the whole group of autoequivalence is now in some cases. So, for instance, in the case of Fano or anti-Fano varieties, when the canonical shift is ample or anti-ample, it is proved that this group, it is precisely the group of all only the trivial ones. The trivial ones in this case. This has been proved in the case of smooth varieties. This was proved by Bondal and Orlov. And has been generalized also for Gorenstein, Fano, anti-Fano. Gorenstein. That was done also by Ballard. And we have an alternative proof, Carlos Sancho and Fernando Sancho. For Gorenstein schemes that are Fano or anti-Fano. In fact, the general idea is these groups is more interesting as your variety has canonical tends to the trivial bundle. I mean, when the variety is Carabillo. So it seems to be especially interesting when your variety has trivial canonical bundle. So in this case, the group has been studied also for some cases in dimension 1, that is for elliptic curves. The group has completely been determined. It's a result by Vandenberg. Let me spell it properly. Yes, H is an R. And the same result has been generalized for the two degeneration of analytic curve that Darío tells us. A rational curve with one node or a rational curve with one cusp. So for genus 1 integral curves, that was proved by Burban and Crozier. A complete description. If we could go to abelian varieties, the group has also been determined. The first results were due to Polychuk, but the complete description was due to Orlov. And there are some results for K-free surfaces, but the group in this case is not completely determined. There are some working on by Daniel Harvitz, Macri, and Stellari. And what else? And yeah, for smooth toric surfaces, this is a very recent work by Bloch and Blumen. I think that's it all in the case of an absolute variety. So let us return to the case of a variety that is fiber over a scheme T. Okay. So if your scheme is fiber over T, so it is quite natural to look at the group of autoequivalencies that are T-linear. So let's say F an autoequivalence is linear over the base if it satisfies the following property. So you have your functor. So for any complex and any complex coming, so let us assume from now on that all our fibrations are flat, okay? Because we're interested in fibrations that are flat and proper morphisms, okay? So from now on, P and T Q are proper and flat. Okay, so here you have the pullback of Ng coming from T, and it has to satisfy that this is isomorphic to the tensor product of that one. So this means that the objects coming from the base go out of the factor. This is the definition of T-linear. Okay? Okay, let us denote by this, like this, the group of this kind of functors. And by projection formula, any of our relative Fourier-Mukai functor is one of these, satisfy this formula. So here you have the group of relative Fourier-Mukai transform. The ones whose kernel is in the fiber product, not just in the direct product. Okay, so this group seems to be quite difficult to describe, and nothing is now for the moment. So it's a good step try to start describing this subgroup. And this is the goal of my talk for those kinds of fibrations. So the goal was to give a description of this subgroup if P is one of the in the title. in the center. Okay, a Weierstrass fibration, an abelian skin, or a Fano fibration. And beyond that, the idea with the talk was to try to point out what is the point in making relative the results. I mean, what do we need in passing from the unabsolute situation where the problem has an answer to a relative one, okay? Okay, so for that, we need our key results that allow us to move from a relative to an absolute situation. Let me state that here. Okay. So, here it is. Okay, let me explain first a little bit. So here the point is the base chain formula. Okay, so everything knows that we have a Cartesian diagram like this one. F, G, G tilde, F tilde. And you have a complex here, and it's always a morphism, natural morphism from here, L, G star, to L, G tilde star, F tilde star of G tilde. And in mild conditions, that when this has quasi-coherent cohomology like this, and one of the two morphisms, either F or G, is flat, then this morphism is an isomorphism. It is isomorphism. And this is unusual because usually people is used to consider flat base chains, but the formula is also true when your morphism F is flat, even if the base chain is not flat. This is good because this allows you to restrict to their fibers. The fibers, you take a smooth closed point here. This is an open inversion, it's an inversion, so it's going to be never a flat morphism, but your fibration is flat. So, if you have now a phantom, okay, let's say with the good conditions, no, the kernel has to be these technical things, no, finite homological dimension over the factors. And you have here a phantom. Then you have all the phantoms induced on the fibers. I mean, you have here the product. That was wrong. You have a closed point T, and you have the fiber of this one, xt by T. Let us denote this gt. And then you have the corresponding integral phantom, phi T, which is the phantom of the restriction of your complex. Here you have your complex, then you restrict it to the fiber. KT. Okay? So, with these conditions, this is a good phantom, goes from the boundary derived category of the fiber to the boundary derived category of the fiber. Okay? And we have nice formulas. I mean, these base chains that I explained before tells you that when you have G, a shift on the fiber, then you extend it by the immersion of the fiber into X. And you apply the whole phantom, then it's the same that this one, phi of G, and also for the inverse image. I mean, you have F on X, both of denoted in the symbol, IS, okay? Then you have phi of G, then you restrict to the fiber, And this is the same, sorry, this is F. This is the same that restrict the complex first and then apply the fan torque between the fibers. Okay? Okay, so with these formulas, we prove, so here is the first key result. So result A was a theorem with Hernández Ruiz Pérez, Fernando Sancho, and myself that proved that the fan torque 5, okay, my conditions, if I remember, it has to be locally projective, and moreover, K finite homological dimension over the two components. Okay, so your fan torque is an equivalence or fully faithful if and only if for all T and T the fan torques induced are equivalences. Okay, and this is one of the main torques that we use in our description of the relative Fourier-Mukai transform for these cases. This is important because it allows to go from an absolute to a relative sitting and vice versa. The important fact it is that going from a relative to an absolute situation, because usually in an absolute situation more things are known. I mean, for instance, for absolute varieties you have a big class of Fourier-Mukai fan torques that are known, that are the twist fan torques along spherical objects. So this allows going from relative to absolute sitting, and here you have the twist fan torques along spherical objects constructed by Seidel and Thomas. So a big class is more now usually in the absolute situation. I by means of this theorem you go from the relative to the absolute situation. On the other hand, this means, this suggests, at least in the cases that we have worked out, that having a description of the autoequivalences of the boundary derived categories of the fibers, you should get some information about this subgroup using that. Okay? But it's not completely clear that you're going to get a complete description of this group. I mean, at least in the case that we have worked out, you need a key property. You need that the kernels all of these fan torques, the relative ones, are just shifted by some degrees. And then we prove the second key results. That tell us that this happens precisely if the same properties holds on fibers. So, key result B, yes, if you have an object here and your X is connected, let me take the right, is connected. If for any T, the restriction of your kernel is just a shift, shifted by some degree that could depend on the fiber, NT for some T, or some NT instead. And KT is a shift on here, flat over the first factor, then the same happens for your kernel. This is just something like that, where key is a shift on the fiber product, and it's flat over X. Flat over X. Okay, so then in our examples, how we get the flatness of the KTs, these ones. Okay, so in the case of Weierstrass fibrations, these KTs are just Poincaré shifts, or universal shifts for certain moduli spaces. Poincaré shifts. So they are obviously flat over there. In the case of abelian schemes, they are, Orloff proof, they are semi-homogeneous shifts. Homogeneous shifts. And using this fact and the generic flatness, we prove that they are flat on an open, and then they are flat everywhere. Okay. And for the third case, the case of Fano fibration, this is trivial, usually, that the kernels are flat. Okay. Well, okay, so let me just. Oh. I don't have much time to explain the result, but let me pass directly to very quickly, the third results that gives you a characterization that one Fourier-Mukai factor is trivial, that tells you that you have K in here, such that for any closed point, the scraper shift goes to the structure shift of another point, closed point. So the kernel of this functor is trivial. I mean, the functor is trivial. Then there exists a morphism from here to here, relative over S, a line bundle on X, such that your functor is just this one. So it's a characterization of when a functor is trivial in some sense. Okay, so let us pass to the case of Weierstrass fibration. Okay, in this situation, then Derrida defines what a Weierstrass fibration is. No? You have the smooth fibers, the generic fiber is an elliptic curve, and the degenerated ones are rational curves with one node or one cast. So we assume that there is a section also. So this is proper and flat with this kind of fibers, and the section, as that you explained, doesn't meet the singular points of the singular fibers. Okay. So in this situation, we have determined completely this group, knowing how is the structure of the group of autoequivalencies of the bounded derived category of the fibers. Okay, C is a fiber, a smooth elliptic, rational with one node or one cast. In this situation, you have the Euler form from, you have here the Grothendieck group divided by the, you have the Euler form defined by the Euler characteristic, no? By linearity. So this is the Euler of F and G. And I induce also a symplectic form here when you divide by the radical of this form. That gives you a symplectic form. And in fact, this group, in the three cases, by means of the rank and the degree, is isomorphic to Z plus Z. Okay? So taking into account that any autoequivalence induce an isomorphism of this group that preserves this symplectic form, and you have a group morphism from the automorphisms to the special linear group. The matrix that has determinant equal to 1 because of that. preserve this. So this matrix is given by the Chern character. So an important thing is that in order to determine this matrix, you just need to know, in order to determine the Chern character of an equivalence, you need to know just the rank and the degree of the transform of the trivial bundle and of the structural shift of any smooth point. This is important to pass from to the relative case. And then the theorem by Hill, Vandenberg, also Biesland, proved that there is an exact sequence like this. The Chern character, and here you have the ones that go to the identity that are the trivial ones. These are the automorphisms of the curve. And you have the shifted by odd numbers and the line bundles of degree 0. Okay? Moreover, from this exact sequence, you get, we proved that it is known, if it was known, that if you have an equivalence coming here, then this kernel is just a shifted by some degree. K on C flat over both factors. Because in fact this is a Poincaré, basically a Poincaré shift. Okay? Taking into account this exact sequence. Okay, and this is the key to pass to the relative situation. Okay, because now, if you want to determine the relative Fourier-Mukai transform, then, okay, let's, by result A plus result B, the first thing that you know is that if you have here a relative Fm, then your kernel is just a shift. Any restriction is an equivalence by A, and then this is a shift flat over X. And this is important. Okay, because why this is so important?
Can you explain? Okay.
Maybe finish and then in the question. Can I? Okay. This is important because now, thanks to the result A again, and one has for any T a morphism like that, restriction morphism. From this one to the auto-equivalence of the boundary derived category of the fiber. Okay. That is given an equivalence just to height. Here you have your Chern character on the fiber to SL to Z, and then you can consider the composition map. So the fact that we prove is that this composition is well defined, and moreover is surjective also. Okay, I don't have time to explain how we prove it, but I mean, it's well defined that it doesn't depend on the T, okay? And this is because of that. So we know that in order to determine the matrix in the fiber, you need to apply the functor to the structural shift of the fiber and to the structural shift of any smooth point. Okay, but using this fact that the kernel is flat over the base, then you get that this rank and degree doesn't depend on the fiber, on T, the rank and the degree, using the fact that the kernel is flat over X. Okay, and how is the behavior of WIT shifts. And for the second one, for the surjectivity, we use again the result A, because here there is a pair of generators. Okay, don't have time to explain that. These two matrices generate this special linear group, and they both come from Fourier-Mukai phantoms that are relative. Okay, this comes from the Fourier-Mukai phantoms of the ideal of the diagonal that Dario tell us. This is the relative ideal of the diagonal embedding, that it is proved to be an equivalence because of result A, okay? And these ones comes from the Fourier-Mukai phantom, which is given by two tensor by this line bundle. Okay? So, this proof basically that this is a suggestive morphism that is well defined, and using result A, we were able to determine which is the kernel of this morphism. So let me just put the result for the fibrations. Okay. So the theorem is the following. If x over t is a Weierstrass fibration, I have to assume that the base is connected. Okay? T connected. Then, the subsequent, there is a subsequence like this one. We have the Fourier-Mukai, the relative ones. Here we have this morphism to the special linear group. And in this case, the kernel is just the relative automorphisms of the fibration, semi-direct product with two-seat tensor over, direct product to the peak 0 of x, where peak 0 of x is just the line bundles such that the degree of the restriction to any fiber is 0. Okay, so it's completely analogous to the absolute situation, but in fact it is key that we need to know how are the kernels of the absolute phantoms. Okay, I don't have time to explain the abelian schemes and the Fano fibrations. Let me just say that we got some results generalizing the work by Orlov in the case of abelian schemes. So basically, we have proof in Solmai, we have to restrict at some point the kind of based scheme to a normal one, because otherwise we were not able to conclude the surjectivity of the subsequence, but we got in some good cases a similar subsequence like Orlov for abelian schemes. And we have also a description for Fano fibrations, allowing in this case singular Fano or anti-Fano fibers. Because in those cases, also the group of autoequivalence was described by Ballard. In this situation, all of them are trivial. So you have a fibration with all those kinds that are Gorenstein, with Gorenstein singularities, Fano or anti-Fano fibers. Then you have a similar result, the group of all relative Fourier-Mukai phantoms, or basically the trivial ones, but I don't have time to explain that one. So thank you very much for your attention.
Any questions?
So
Yes.
This relative Fourier-Mukai transforms, how far is it from the automorphisms of derived group, derived category in the Weierstrass?
We don't have idea. In fact, the only example that we know is the case of Fano varieties. They are, in fact, all the linear autoequivalence or in fact relative Fourier-Mukai transform. But I don't have idea how far the subgroup is from the group, the total group. At least only in this case. They are precisely in that case, all of them, they are relative Fourier-Mukai factors.
So if you have the smooth family with locally projected fibers, you're saying that the kernel of the autoequivalences over the generic fiber is given by a sheaf. And you're also saying over the special fibers?
No, it's not enough with the generic fiber. You have to know it over every fiber.
So the theory which you used, that
The theorem, in fact,
it
yes.
did not assume that C is.
Yeah. No, that one. No, because this exact sequence in the case of in the absolute seating, it was proved by Burban and Krosler for the nodes and the cast. Okay.
So for them also every autoequivalence is to be given by
Yes.
shape, right?
Yes. Yes. Yes, it's basically the same result. It's again a universal shift for some moduli problem. In the case of the node and the cast. It was proved by Burban and Krosler.
So in the
Yeah.
most simple case, I want to understand this. If I have a family that degenerates over something singular,
Yes.
and over the generic fiber, I know this kernel
No.
sheaf. Can I relate it to the same
No.
sheaf over the kernel?
No, in fact, we were trying, just to let you know, just in case you want to generalize this, for more degenerated fibers, we were thinking about the generalization when one of the fibers of the elliptic fibration is one of the Kodaira fiber. I mean, when you have, for instance, a cycle of projective lines as a degenerated fiber of an elliptic curve. Okay? So in this situation, you can find Fourier-Mukai functors whose kernel is not just a sheaf, but a genuine, a real complex with two non-zero cohomology sheaves. And in this case, we are not able to apply our machinery. Okay?
Just a second. So what you've just said, does it mean that over every other fiber, you have an object which restricts the shift to every fiber except this singular one, where it becomes a complex, right?
Yes. Look, if you have this as a special fiber of a smooth surface, okay? This is just the fiber over the zero. Okay? And then you take an irreducible component of that one, C. Okay? C is a -2 curve and it's a rational. It's P1. Okay? And if you consider this object, the structure shear of this reducible component, and you push it to the surface, that gives you an spherical object. Okay?
Yes.
Because of these two conditions. Okay, so that's defined by Seidel Thomas' work. That gives you a twist phantom, which is an equivalence. Okay, this is a Fourier-Mukai phantom whose kernel is a complex. Okay, because this is a smooth surface. Okay. Okay, this is a relative Fourier-Mukai phantom. The kernel is just supported on the fiber product. Okay, so this phantom on its fiber for T not equal 0, this is trivial. This is the identity phantom. But for the special fiber, this one, this is a phantom whose kernel is a complex with two non-zero cohomology sheaves. It's not a sheaf anymore, using our results. So there is some work to do, how to change the method in order to get some more information. So it's not completely directly that from the knowledge of the autoequivalence of the boundary derived categories of the fibers, you get how is the groove of relative Fourier-Mukai phantoms. It's not trivial. I mean, there is some work to do. Okay.
No questions? Thank you for the speaker again.
you.